All right, so the first the warm-up right here is graphing the 8 functions that we talked about yesterday, minus the constant function, because that's so easy, like, we're not going to have you practice that right now. So go ahead and pause the video, do them as quick as you can, okay? Try to do it in under 90 seconds. That's how fast I want you to try to do it. All right, so write the equation of each parent and graph it accurately. So I'm going to go quick. I have f of x equals x. Quadratic is f of x equals x squared. Cubic, f of x equals x cubed. Cube root, f of x equals the cube root of x. Square root, f of x equals the square root of x. Absolute value, f of x equals the absolute value of x. Exponential, f of x equals 2 to the x. And logarithmic, f of x equals log base 2 of x. All right, so we're going to graph quickly what each of these look like here. So we have a linear function. These are my critical values, and then I'm going to graph the line. Critical values for quadratic, and then I'm going to graph the parabola. Cubic, these are my critical values, and then I'm going to graph my cubic function. Cube root, same critical values, but this is like this. It's a root. Square root, these are my critical values. Absolute value, here are my critical values, but it is V-shaped. So same as the parabola, but V-shaped, not U-shaped. My one critical value, and we should say that our other critical value technically is this asymptote right here. While I have my red pen out, I'll draw my logarithms asymptote. Okay, and critical value, I already drew 0, 1, and then it goes up and to the right. And this one, 1, 0, up and to the right. All right, there's your quick sketch of what your functions look like. If you don't know them, you gotta know them. Okay, so what we're gonna talk about, so we already did translations yesterday, which is moving your graph up, down, left, or right. So what we're gonna talk about next, which is very hard for me to talk about in a video, I'm not gonna lie, so I'll do my best. You guys have to listen to my words here, but we're going to first talk about dilations, vertical and horizontal dilations. This column right here are the words that we will use. So words we will use, ... Okay, that column are the pre-calculus vocabulary words that we will use. We will not call them anything else that we make up, okay? So definition, remember, is what the equation looked like. So the first two are vertical compression and a vertical stretch. So the equation for them looks similar, okay, or they look the same. So I'm going to write that down. So that's when you have a function, and then for a vertical stretch or a vertical compression, you're going to see a coefficient in front of your parent, okay, in front of your parent. So what I mean by that, let's look down at these right here, is that here's my parent x squared, and there's a coefficient in front of my parent, okay? So that is either a vertical stretch or a vertical compression. So we're going to use the letter A. We're going to use the letter A for whatever that number is in front of your parent, and then you will have times, the dot won't be there, it'll just imply whatever your function is, okay? Now, for a vertical compression and a vertical stretch, so I'm going to duplicate this. That's exactly the same. Now, how do we know which one it is? Okay, so what you're going to do is you're going to look at that A value. If the A value is in between 0 and 1, okay, so that means it's, I don't want to call it a fraction because 7/2 is a fraction and 7/2 is in between 0 and 1. Any number in between 0 and 1, a lot of people associate this with a fraction, like a half, a third, 2/7, but not 7/2, okay? A decimal, people say a decimal. 1.6 is a decimal. That's not in between 0 and 1. So a number in between 0 and 1, okay, that is going to be a vertical compression, vertical compression. If that value, A, is greater than 1, that is going to be a vertical stretch. So if it's a 3 or a 6 or a 17 or a 9.47, then it's going to be a vertical stretch. okay? Now, when we're looking at this, we're looking at the absolute value of that number. It does not matter if it's positive or negative. We'll talk about what the negative does. It does nothing to do with the stretching or compressing. Okay, so description is what it's going to look like. So if you have a vertical compression, that's our first one right here, vertical compression, okay? So think of taking something and then think of taking your hand on the top of it and the bottom of it and compressing it, bringing it together. Okay, I'm doing it with my hands right now. What happens to what's in my hand, or what's in my hands? Does whatever's in my hand get wider or narrower? Okay, so think of a parabola, let's say. If I put my hands here and here and push it this way and push it this way, is the graph going to get wider or narrower? The graph is going to start coming out this and this way, right? So it's going to get wider. It's very hard to do this without you seeing my arms, okay? Now, if I vertically stretch it, so instead of compressing it, I'm stretching it. So what I'm doing is I'm taking this and pulling it this way. I'm taking this and pulling it this way. Is the graph going to get wider or narrower? It is going to get narrower. So that's what it looks like. Those are the words we used to use in integrated and algebra 2. A sketch of this, okay? So I need an original first, so I'm going to draw, let's just use a parabola like I was using, okay? So let's say we have a parabola like so. I knew that was going to happen. So let's say we have a parabola like so. I'm going to copy this. Copy, and then let's paste this in each one of these. Paste, paste. That way I don't have to draw it 4 times, okay? All right, so if there's a coefficient in front of your parent and it is a number in between 0 and a, your graph would get wider. So instead of looking like what I have drawn, it would get wider, like so, and that's called a vertical compression. If that a value in front of the parent was a bigger number, like 3 or 6 or 14, or even -6, because you're taking the absolute value of it, it would get narrower, and that is called a vertical stretch. Okay? All right, now let's talk about horizontal compression, horizontal stretch. So what would that look like? Once again, the equations look the same. G of x equals, this would be inside the parent. So if you saw the parent, absolute value, whatever, and then there's a coefficient in front of x, x is being multiplied by. Okay, and we can call that a. We could actually call that something else if we wanted, but I'm just going to keep calling it a. And then for horizontal stretch, it'd be exactly the same. So let's duplicate that. Now, for a horizontal compression, okay, that would be if a is greater than 1. So if you had a 3 inside, you might be saying like, oh, a 3 outside, that's a vertical stretch. Well, that's a horizontal compression if it's inside, okay? And then idea here is that if that a value, once again, absolute value here, is in between 0 and 1, if it's a smaller number, that is a a horizontal stretch. All right, what does that look like? A horizontal compression, all right? So now, let me get my drawing back here, okay? So here's my parabola. If I horizontally compress it, so if I push in it this way and this way, is it going to get wider or narrower? Narrower. Okay, and then if I horizontally stretch it, meaning if I pull on the sides this way and this way, if I stretch it horizontally, does it get wider or narrower? Wider. So when I have a horizontal compression and I compress it horizontally, it's going to be narrower. When I have a horizontal stretch and I horizontally stretch it, it is going to be wider. So what I want you to notice is that vertical compression, horizontal compression, wider, narrower, okay? You can't just say, oh, compression is wider. No, that's not how it works. You have to think about it, okay? All right, so I know that was pretty quick, but let's do a graph of each, okay? Make sure we know the difference between the two. Oh, before we move on to this, here's how I help myself memorize this, okay? Because yes, I got to do something to help myself, right? I looked at all of the notes and all of the homework and all of our tests and all of our quizzes and our final exam, and I said, which one do I see the most? That's what I did as a favor to all of you. Which one do I see the most? The answer is vertical stretch, okay? So what I do is I memorize what a vertical stretch looks like. That helps everything else to fall into place. So a vertical stretch, once again, is when you have a coefficient in front of your function and it is bigger than 1, okay? So if I see a 3 in front of my parent function, if I see a 17 or a -6, because remember absolute value, it's bigger than 1, okay? That is a vertical stretch. Now, if it's smaller than 1, or in between 0 and 1, I should say, that is still a stretch, but it is that is still yes, it's still vertical, but it is a compression, okay? Now I do the opposite for thinking about horizontal stretches and compressions. And I say, okay, I know that a 3 in front of the parent is a vertical stretch. So a 3 inside the parent is a horizontal, not stretch, compression. Okay, that's how I help my brain memorize it. Let's see if it helps you. I don't know. Okay, so graph each of these. We're going to start with our quadratic here. We're going to graph the parent. Remember, it's U-shaped, so make sure you're drawing a U and not a V. And once again, this is the parent. This should say graph each function and describe the transformation. We always ask you how it looks, so we need to do that, okay? All right. So this first one right here, here's the parent, x squared, and then this is a coefficient in front. Here's the parent, and here's a coefficient in front. Notice this is inside the parent, inside the parent. So in front of the parent is vertical. Both of these are vertical. Vertical, vertical. And now I have to know which one's which. So I'm going to go back to my brain and say, wait, I memorized this. A number bigger than 1 is a vertical stretch. A number smaller than 1 is a vertical compression. See that? Okay. All right, so now we could just say vertical stretch looks like this. It's skinnier, right? We could do a sketch of it. We allow that as long as it's inside this 1, 1 and -1, 1. We allow that when you're actually doing these. But just to prove it to you, let's plug in 0, -1, and 1. So if when I plug in 0, I still get 0. When I plug in 1 this time, 1 squared is 1 times 2 is 2. So notice these points move up here when they were originally here and here, which they're not there anymore. And this is more narrow than the parent. This is more narrow than the parent. If I plug in 0, I get 0. If I plug in 1, I get a half, and then the reflection. So notice this is wider. If you look at it, it is a vertical compression. Looks like someone sat on it. Okay? All right, let's make sure we understand this. So notice there's a coefficient in front of x, but it's inside the parent. Inside is horizontal. Okay? Outside is vertical, inside is horizontal. All right, so I say, okay, I have this memorized. If the number is bigger than 1, it's a stretch, but that's for vertical. So if it's bigger than 1 and it's for horizontal, that means it's the opposite of that. It's compression. That's how my brain does it. And this is a horizontal stretch, that means. See that? Okay? If you think of another way to help you get it, that's fine. Once again, if I wanted to say horizontal compression, so think of taking your hands from the left and right, bringing it in. Ooh, it gets narrower, and you want to do a sketch of something narrower, with arrows on the end, of course, we would take it. But just to prove it to you, let's plug in 0, 1, and -1. Plugging in 0, you get 0 squared, which is 0. Plugging in 1, you get 2 squared, which is 4. And there's its reflection. So notice, much more narrow. Plugging in 0, you get 0. Plugging in 1, you get a 4th, and its reflection. So way wider, which is a horizontal stretch. It's like you took the sides and pulled them out. Okay, last type of transformation we have to talk about is reflection. We have 2 types of reflections. We have vertical reflections, and we have horizontal reflections. Vertical reflection, so these are the words we're going to use, vertical reflection and horizontal reflection. Definition, what's the equation going to look like? So vertical reflection, since it's vertical, remember, vertical is on the outside of the parent. So you have f of x, right? It's not on the inside, it's on the outside. And for a reflection, it's the opposite of those values. So you're going to see a negative in front. For horizontal reflection, remember horizontal is on the inside of parents. So this is going to be on the inside of the parent. And once again, to reflect it, you take the opposite, so negative x. Okay? Description of a vertical reflection, it's a mirror image of that function over a horizontal line. Now you might be saying, wait, vertical, how can it be a mirror over a horizontal line? So here's a horizontal line. If I want to take a vertical reflection of this, it would go over the horizontal line. See that? All right, now for a horizontal reflection, it's a mirror image over a vertical line. All right, let's use, well, since these are all square roots, let's use square roots. So let's do the parent of a square root looks like this. I'm going to go ahead and copy that. Okay. All right, so a vertical reflection, imagine a horizontal line you're reflecting over it. So it will be like this. And for a horizontal reflection, imagine a vertical line and a reflection over it. So our vertical line's right here, reflect over it. And you got this right here. Okay, so we're going to graph each of those. We're going to graph, we just did that, but just making sure we know which one's which, okay? So this is our parent. If you look right here, this is outside. Outside the parent function is vertical. So this is a vertical reflection. This is inside the parent, still the opposite of it, so it is a horizontal reflection. All right, our parent, remember 001142. Okay, so now we're going to do a vertical reflection. So we already know what a vertical reflection looks like. It looks like this. Okay, but just to prove it to you, let's plug in 0. If you plug in 0, you still get 0. If you plug in 1, square root of 1 is 1, but then you take the opposite. Plug in 4 is 2, but you take the opposite. So notice that's what your vertical reflection looks like. Okay. All right, when we plug in 0, negative 0 is still 0, square root of 0 is 0. We plug in 1, we get an imaginary number. Can't do it. So we can plug in negative 1 instead. Negative 1 is positive 1, square root of that is 1. Plug in negative 4. Negative 4 is positive 4, square root of that is 2. And that's why it looks like that. Okay? Okay, so now we're going to throw this all together, right? We have 3 graphs to do. You have to state what the parent is, describe each transformation, and then graph it. Notice it also says for C right there, you're not just graphing the new function, you're going to graph the parent with a dash curved, and then you are going to graph the new function with a solid curve. Okay? All right, so first off, what is the parent? So if you look right here, this is x cubed. So my parent is x cubed. And I'm going to start by graphing the parent. So I'm going to do 0, 0, 1, 1, negative 1, negative 1, and then dashed. That's good enough. And that's good enough. Okay, there's the parent. Done. All right, now I'm going to describe each transformation. So I like to move left to right when looking for them. So first off, I see this negative in front. So I say, okay, it's in front of the parent, and I'm going to call it number 1. It's in front of the parent, so it's vertical. And since it's the negative, that's a reflection. This is a vertical reflection. All right, now I'm going to move on to the next one. I see a 2 in front of the parent. So I should say outside of the parent. Outside of the parent. What's inside the parent? This is inside the parent. Inside the parentheses, okay? All right, so inside or outside the parent still, so we're still vertical. And then remember, a coefficient in front that's bigger than 1 is stretch. Pay no attention to the negative, right? You're just looking at the 2. All right, next, I'm moving inside the parent. Okay, so this is inside the parent. That's horizontal. I'll call this 3. And then remember that number being added or subtracted off of x moves it left or right. So this is a horizontal translation. And horizontal translations are always the opposite of what you think. So -1 is actually right one. All right, and then the very last one is this -3 on the outside. So this is outside the parent, so vertical. Once again, translation because it's added or subtracted. And it does exactly what you think it does. So it's -3, so down 3. All right, now we just need to do a sketch of this, and this problem will be done. All right, so what you're going to do is you're going to start off by using your translations to graph your new 0, 0, okay? So right 1 down 3. Right 1 down 3 is right here. So there's my new 0, 0. Now, usually, I'm going to end up erasing these, but I want you to see what I'm talking about. Usually, I have a point here and here to make my cubic function, but I need to vertically reflect them. So I'll do that right now. So I'll vertically reflect them. So now they're here and here, right? But I also need to vertically stretch them. So thinking about taking something and stretching it vertically, pulling on the top and the bottom. Does it get wider or narrower? It gets narrower. So instead of going through this point, or instead of, I'm trying to delete there, or instead of going outside this point because that's going to get wider, you're going to go inside that point. And I'm going to do the same thing here because that's going to vertically stretch it. Erase those 2 points that are not part of the graph. And there you go. Now, if you're not sure if it looks wider or narrower and you want me to know it, you can put narrower right next to it. And then I say, okay, I know they're trying to make it narrower. Got it? All right, let's move on to the next one here. So I need to know the parent first. So I look and I see a square root. So my parent function is a square root function. I'm going to graph my critical points. 0, 0, 1, 1, 4, 2. Dashed curve. All right. So let's see what's happening here. So first off, there's nothing in front on the outside. So I can move on to this inside right here. Call that number 1. So that's inside the parent, so it's automatically horizontal. Negative in front is a reflection. All right, we're going to move on to number 2 right here, which is this -2. It's still inside the parent, so it's horizontal. And it's added or subtracted off of the function, so that is a translation. And remember, horizontal translations are the opposite of what you think, so -2 is right 2. And then last but not least, we have this +1 on the outside. So remember, outside of the parent is vertical. So this is vertical. Still being added or subtracted, so that's translation. And it's exactly what you think it is, which is up 1. All right, so let's start with that critical point of 0, 0. I can see it's moved right 2, up 1. Right 2, up 1, so now it's here. And then there's a horizontal reflection. So remember, usually the points would be, there'd be a point right here, and then it would look like this. But I have to reflect this horizontally, okay? So think of a vertical line, which should be right here. And then you got to reflect over that, okay? So keep backing up here. This point comes here. And then we can go ahead and draw it. If you want to draw where 4, 2 would be, which is up 1 over 3, like right here, you can. But if it's not perfectly accurate, you're not going to get points taken off for that. Okay, but you do want these 2 points accurate. Okay, moving on to our final graph. If you want to pause the video and try yourself, I think that's a fabulous idea. All right, so we'll start with the parent. Absolute value function. 0, 0, 1, 1, -1, -1, V-shaped. Oops, I forgot to make it dashed. There we go. That's what the directions say, right? Okay. All right, now let's describe our transformations. We're going to go through one each, but I'm going to start all as far left as I can go. And I see a 3 here. That's outside the parent. Okay, so outside the parent is vertical. And then a multiplier in front that's greater than 1 is a stretch. See, we've seen vertical stretch twice. We haven't seen vertical compression, horizontal stretch, horizontal compression. Just in these notes right there, right? So that's why I said you see these the most, because it's true. All right, we're inside, so horizontal. It's being subtracted, so that is translation. And opposite of what I think, so right too. And then the last one, right here. Outside, so vertical. Subtracted, so translation. Down one. All right, let's graph this. 0, 0 is now right 2, down 1. Right there. Okay. And right 2, down 1. Yeah, that's right. And then what else? I need a vertical stretch. Okay. So let's think about what a vertical stretch. If I wanted to vertically stretch this, I'd pull these up. I'd pull this down. Right? But obviously 0, 0 is going to stay where it is. But I mean, like, think about that. Okay. And get narrower. So I'm going to make this narrower. So instead of going through this point and this point, which is where it would be, I want it to be going closer than that. So here and here, I'm going to say. Okay? All right, that's it for today's notes. You can go ahead and get started on the homework.